Hey, Gio, I don't like how those clouds look. I've never really been that fond of rain. Water and computers just don't mix.
Right, but almost every plant and animal on the Earth needs water in order to survive.
Well, that might be true, but computers still don't have to like it.
No, but it never hurts to know more about it. Why don't we connect our databanks and explore a process called the water cycle? By the time we're through, you might even appreciate water for the amazing, powerful resource it is. Iggy, water is very important to life on Earth. Plants take in water through their roots, while animals need to drink it in order to survive.
With all those animals and plants needing water, I guess there's a lot of it on the Earth, right?
There sure is. Almost 3/4 of the Earth's surface is covered by water.
Is that why the Earth looks so blue from outer space?
Exactly, Iggy. Almost all of the Earth's water is the salt water that's contained in the ocean. That's fine for the animals that live there, but ocean water is too salty for people to drink.
So how much fresh water is there?
Actually, Iggy, I'm going to need a little help on that. My files aren't complete.
Then let's call up the Kids Into Doing Science Club for more information.
Hello, Kids Into Doing Science. This is Sarah. How may I help you?
Hello, this is Gio and Iggy. Would you have any good demonstrations to show how much of the Earth's water is fresh water?
Sure, just let me get the files. Okay, here's an easy way to picture all the Earth's water. Imagine you have 100 large cups, and each cup is filled with water. If these 100 cups held all the water on Earth, only about 3 cups would hold fresh water. All the rest would be salt water. Let's go further. Take your 3 cups of fresh water and use all the water in them to fill 10 smaller cups. Now freeze 8 of the smaller cups of water, because that's how much of the Earth's fresh water is frozen as ice and cannot be used by plants and animals.
Hey, there's not much water left.
Now, take a small eyedropper and fill it from one of the last 2 small cups of water. The water in the eyedropper represents the usable fresh water that's above the surface of the Earth, in lakes, streams, ponds, and rivers. The rest is underground.
But what happens when a little bit of water gets used up?
It won't, and that's the most marvelous thing about water. The Earth has about the same amount of water now as it did millions of years ago. It just keeps getting recycled over and over again.
Thanks for the help.
You're welcome. Bye.
Bye! When it comes to recycling water, no people are necessary. You'll understand better as we take a look at the 3 stages of what is known as the water cycle. It all begins with evaporation.
Evaporation?
Evaporation. Here's an example. When this swimmer gets out of the pool, his body is covered with liquid water. But if it's a warm, sunny day, soon the liquid water dries off his skin. That's evaporation. Evaporation occurs when liquid water turns into water vapor, and it is constantly happening around the world. Wherever water and air touch, some water is always moving off into the air as water vapor. Evaporation can happen when things are cold, but it happens much faster when things are warm. Do you know what warms things and speeds up evaporation?
That would be the sun.
Yes, the energy from the sun warms the water and speeds up evaporation. The sun provides the energy to start the water cycle through evaporation.
Wow!
Of course, water is evaporating everywhere, from oceans, lakes, streams, plants, and even out of the soil.
Geo, something's been bothering me. Since people can't drink salt water, all that salt water in the ocean is pretty much wasted until it evaporates, right?
Well, Iggy, the ocean provides many wonderful benefits to people and other living things. Oceans are the biggest source of evaporation on Earth and are alive with plants and animals that can be sources of food. For many thousands of years, ships have sailed over the ocean carrying people and things all over the world. Currents in the ocean help cool off the air over hot parts of the world and help warm up the air over colder parts of the world. In addition, ocean waves constantly reshape the coastlines too.
Gee, I had no idea how special the ocean really was. Okay, Geo, let me see if I've got all of this right in my memory banks. We have a whole lot of water on the Earth, and most of it is salt water in the ocean. And we've got the same water on Earth that has always been here. It just gets recycled through a process we call the water cycle, which begins when the sun evaporates the water, turning it into water vapor. It's all downloaded into my memory banks. So what else happens in the water cycle?
Condensation, Iggy. Condensation is how the water vapor, or gas, gets turned back into liquid water. Let me ask you a question. If it takes the heat from the sun to turn water into vapor, what might be a good way to turn water vapor back into liquid water?
You turn off the sun, at night?
Good thinking. But condensation can take place during the day or at night. Basically, anytime the air containing the water vapor cools. Cold air can't hold as much water vapor as warm air. As the air first begins to cool, the extra water vapor starts to form teeny tiny drops of liquid water. That's what clouds are made of. Wherever the air cools, you get condensation. You can see this happening on the outside of a cold drinking glass on a hot day.
So we've got evaporation and condensation, the liquid water turning to water vapor and back again. Is that the whole water cycle?
Not quite. Iggy, you've seen that tiny water droplets can remain in the air. But what do you think would happen if these droplets got a lot bigger?
Well, I guess the water would fall.
Bingo! The final step in the water cycle is precipitation. This is how the water droplets get from the air back down to the earth again. When the droplets get too large and too heavy to stay in the air, they fall as rain. If things are cold, the precipitation might be snow, sleet, or hail. But it is always fresh water because only pure water vapor was in the air to begin with. Let's watch this process in action.
Today, we're going to demonstrate how the water cycle works by creating our own mini water cycle in a bowl. You'll need a large, clear glass bowl, a small bowl, a pitcher of clean water, salt, a spoon, plastic wrap, a ruler, and a small marble. First, slowly pour the water into the big bowl until it's about 1 centimeter deep. Now, add a few dashes of salt into the water. Stir the water with your spoon until all the salt grains have disappeared. This means that the salt grains have dissolved into the water. The water is now salt water. Taste it. It's salty, right? Next, place the small bowl in the center of the large bowl. Then cover the large bowl with plastic wrap. Be sure the wrap clings to the sides of the bowl. Gently set your marble on the center of the plastic wrap. Make sure that the marble is directly over the small bowl. This should cause the wrap to sag just a little right over the small bowl. You'll see why this is important in a moment. Carefully move your bowl to a warm, sunny spot for a few hours.
Oh, I see what they're doing now. The salt water in the bowl represents the ocean, and the sunshine will evaporate the water.
Exactly!
After a few hours, check your bowl. You should see that some changes have occurred. First, there will probably be water droplets clinging to the bottom of the plastic and sides of the bowl. Second, there should be water in the small bowl that wasn't there before. Remove the marble and plastic wrap and taste the water in the small bowl. It should not be salty. It's fresh water.
And how did this happen?
Sunlight heated the water inside the bowl, causing some of the water to evaporate and form water vapor. This is similar to the way ocean water evaporates when heated by the sun. When the water vapor touched the plastic and sides of the bowl, it cooled and condensed. The drops that condensed on the underside of the plastic wrap slid down the wrap to its lowest point, under the marble. When enough water collected there, it became too heavy to cling to the wrap, and fresh water dripped into the small bowl.
Very cool! Evaporation, condensation, and precipitation. The water cycle, all in one bowl. The sun warms water and evaporates it, turning it from a liquid to a gas called water vapor. The water vapor cools and condenses into droplets, and the droplets become too heavy and fall back to the earth as precipitation.
Precipitation is the last stage in the water cycle, but all the water that falls as precipitation doesn't evaporate again right away. Iggy, remember how the Earth's fresh water might be pictured in 10 little cups and 8 of them were frozen? Much of the Earth's fresh water is frozen into ice. In some very cold, snow-covered places, like at the Earth's north and south poles, the ice caps never melt. The ice piles up year after year and can't be used by plants or animals.
Okay, so where is all the Earth's usable fresh water?
Part of it is on the surface of the land. Remember that eyedropper full of fresh water? Well, there are different places this water can go on the Earth's surface. When rain falls on land, or when snow, sleet, and hail melt, much of the water soaks into the soil. But once the soil holds all the water it can, the rest of the water begins to run off. It collects into little creeks that join to form streams. And streams can join to form powerful rivers. The water in rivers and streams moves towards the ocean. Along the way, however, the fresh water in rivers and streams is used by all sorts of animals and people. Often, small towns and large cities are built along streams and rivers. The water in them gives people drinking water for their homes and water for their businesses. Farmers often use rivers and streams as a source of water so that their crops can grow.
So is all the fresh water on the Earth's surface flowing in rivers and streams?
No, not at all. Sometimes the precipitation that falls on land collects and forms ponds and lakes. Some lakes are huge. The Great Lakes in North America are hundreds of kilometers long and wide.
Water in rivers and streams, ponds and lakes. Got it. Saved to memory.
Of course, people also use dams to trap river water in artificial lakes called reservoirs. Reservoirs are great sources of fresh water, and water spilling out of dams is often used to provide energy.
Gio, you said that most of the fresh water that falls as precipitation soaks into the ground.
You bet! And that's why water under the ground, called groundwater, is one of the most important sources of fresh water for people, especially in areas that don't get a lot of precipitation.
But how does it get into the ground?
When precipitation falls on the ground, a lot of it remains in the soil. The soil soaks it up like a sponge, but a lot of it keeps moving. It sinks slowly down through the ground as far as it can go.
What do you mean as far as it can go? What stops it?
It stops when it meets a layer of rock it can't pass through.
Sort of like an underground dam.
That's right, Iggy. This groundwater then fills up, forming an underground reservoir. People sink wells into these underground reservoirs to get this water. But it can also leak out of the ground through natural springs. As an underground reservoir fills, the level it fills to is called the water table. The water table can move up or down as the underground reservoir gets more water or loses water. If the water table gets too low, springs dry up and wells stop pumping water.
So underground reservoirs can run out of groundwater.
Yes, they can. And when they do, they often leave behind some interesting formations. Let's take a look at one.
Have you ever visited an underground cavern? All over the world, caverns such as Carlsbad in the United States and Xelha in Mexico's Yucatan Peninsula allow visitors to make their way through underground chambers that have been naturally created over millions of years. But have you ever wondered how these caves were created? Believe it or not, all of these interesting formations were created by a little water. When pure water falls as rain, it travels through the soil and underlying rocks. By the time water reaches the reservoirs that lie deep underground, it's no longer pure. As rain falls through the air and soaks into the soil, it picks up small amounts of a gas called carbon dioxide. And as this gas dissolves in water, it creates acids that have a great effect on rocks that lie below the soil, especially limestone. The acids will slowly dissolve the limestone as they flow through, creating caverns such as these that can reach for many kilometers. But even as a cave is formed, water continues to seep down from above. The dripping water leaves dissolved minerals behind as crystals of limestone. Little by little, these crystals can add up to build very interesting shapes, such as stalactites that reach down from the ceiling, or stalagmites that reach up from the floor of the cavern. So if you ever get a chance to explore one of these natural underground wonders, keep in mind how they were created over many millions of years and how they're still forming, one drip at a time.
So, in reviewing my memory banks, I see we've got the Earth's fresh water in several forms: frozen water, water in rivers and lakes, and groundwater. And even though it's only a small part of all the water on Earth, it still seems like a lot.
It is, if people use it wisely.
What do you mean? Since water is recycled all the time, how could people use it unwisely?
Well, as you've seen, people can use too much underground water and empty the water table. If they live in an area that gets very little precipitation and has no rivers, then they're out of water. But there can be another problem that can exist in areas with plenty of water. It's water pollution.
You mean dirty water?
It's more than that, Iggy. Many things can pollute water, and some of them can be very harmful to plants, animals, and people. Oil can run off the streets into fresh water supplies above and underground and later into the ocean. Oil can also be spilled at sea. Sprays that farmers use to protect their crops from insects can also get into these waters where they can harm fish and other living things.
Yipes! So the Earth's water is being ruined?
Well, people are learning all the time how to better protect their water from pollution and how to clean up water if it does get polluted. So, Iggy, your memory banks must be full of water now, so to speak.
I sure have stored a lot of information. I've learned that water is very important to animals and plants and is recycled through evaporation, condensation, and precipitation. I know that most of the Earth's water is salt water and that most of the remaining fresh water is frozen in ice or underground. The rest is water found in rivers and streams or water found in lakes and ponds.
And now I have to ask, have you learned to appreciate water?
Yup, just like you said, it's amazing and powerful, and it's renewed all the time. Why, if I weren't a computer, I think I'd want a drink of water right now. But in the meantime, I'll settle for some cover. Geo. Check out what I'm picking up from one of our remote field cameras.
Ah, a small rock slide, which happens to be a great example of weathering, erosion, and deposition at work.
Weathering, erosion, and deposition? Gee, those guys sound pretty important.
Weathering, erosion, and deposition are very important, Iggy, but they're not people. They are forces that naturally change the Earth's rocks and soil. Let's merge our data banks so I can fill you in on these processes which have shaped the Earth's surface for millions of years. Iggy, weathering, erosion, and deposition are natural processes that are wearing away at the Earth's rocks and soil all the time. Weathering is the way rocks get broken into smaller and smaller pieces, sort of like what this girl is doing here with hard dirt. Except that weathering usually happens much slower, taking many, many years to occur. When the pieces of rock get carried away to other places, we call it erosion.
I see, sort of like a kid moving broken up pieces of dirt.
And when these pieces of rock and soil are placed or deposited in a new location, we call it deposition.
Oh, like where the kid drops the broken pieces of dirt in another spot.
Very good, Iggy. Weathering is happening all the time, everywhere on the Earth's surface, but it is usually a very slow process. If a person spent his whole life living in one house with a big rock in the backyard, he would probably never see any noticeable changes in the rock's appearance.
Then how do we know weathering happens at all?
Sometimes you can see it in action. Remember the rock slide?
Oh, yeah.
And we can see what weathering has done in the past. Look at these rocks. They were shaped by weathering.
So what makes weathering happen? I thought it might have something to do with the weather. But when I think of weather, I think of rain, snow, wind, stuff like that.
Very good. Those forces and others cause weathering in two ways: physical weathering and chemical weathering. Physical weathering is how rocks get cracked, broken up, and worn down through physical action. Iggy, have you ever heard of something called abrasion?
Isn't abrasion what happens when kids fall down and scrape their knees on the sidewalk?
Yes, it is. In fact, the abrasion that happens to those knees is a lot like the abrasion that happens to rocks because of solid particles carried by water and wind. Have you ever seen a painter sandblasting away old paint? Small sand particles are used to scrape the old paint away. Although it acts much slower, wind-blown sand can do the same thing to rocks. Look at these unusual rocks. They were shaped by abrasion. Thousands of years of scraping from wind-blown sand.
Wow, natural wind art.
Yes, and moving water is even more powerful, as it can carry larger rocks as well as sand and mud. These rocks pound and grind away at each other, and anything they move over. This happens in rivers and at seashores, where the waves pound the land. That's why you'll find so many rounded stones in these locations. The edges of these stones have been worn smooth by all the grinding.
Looks rough.
It is, and it goes on night and day. In fact, the change from night to day is another cause of weathering.
Why's that?
Actually, Iggy, I'm going to need a little help on that. My files aren't complete.
Then let's call up the Kids Into Doing Science Club for more information.
Kids Into Doing Science, I'm Alan. I'll be your guide today.
Hi, it's Iggy and Geo again.
We need more information on how the change from night to day can break up rocks.
Sure, just let me get the file. Though you can hardly see the change,
heat makes rocks swell or get larger, while cold weather makes them shrink. After a long, cold, dark night, the warm sunlight can cause rocks to crack. If water gets into the cracks, it can cause more problems when the cold night comes again. You see, when water gets very cold and turns into ice, it actually swells or expands.
Really?
Yes, you can test it. Take a 1-liter plastic water bottle and leave it in the freezer overnight. In the morning, check it. The water bottle will be swollen because the ice inside it is bigger than the water was.
Okay, but that's a thin plastic water bottle. What can ice do to rocks?
Expanding ice is very strong. It can easily widen a crack in a rock. All this swelling and cracking is one reason you often see piles of broken rock at the bottom of rock cliffs. The rocks crack off and fall to the ground below.
Wow, that's cool. Or cold.
Glad I could help. Talk to you soon.
Geo, the swelling of ice can really cause problems for rocks, can't it?
That's right. So sometimes people try to protect rocks from being damaged by ice.
What kind of rocks could be so important?
Well, let's take a look.
This is Mount Rushmore National Memorial in South Dakota. Mount Rushmore is the world's largest sculpture and features giant carvings of the faces of 4 United States presidents. Representing many years of hard work by hundreds of people, Mount Rushmore is an extremely important national treasure. But the giant carvings are in danger of changing due to weathering. You see, even though Mount Rushmore is made of an extremely hard rock called granite, it has natural cracks because of the way it formed. Granite forms from volcanic activity, when hot melted magma pools up and cools deep underground. After thousands or millions of years, as the layers of rock above the granite are worn away, the granite dome or mountain is exposed. As the rock is now exposed to the forces of weathering, the granite swells a bit and cracks. Workmen did the best they could to fill and patch these natural cracks as they carved Mount Rushmore. But water still gets into the crack and freezes. So while granite is an incredibly strong type of rock, ice can create the kind of force needed to break the rock. Let's see that in action. Here is a granite cylinder that has been drilled so it can be filled with water. Extremely cold liquid nitrogen is being sprayed over the cylinder to freeze the water in it. And look what happens. As the ice forms, it swells and shatters the granite. This same thing is happening on a much larger scale on Mount Rushmore. When water gets into the natural cracks in the rock, it can freeze and make the cracks larger and larger. Here you can see a long crack on George Washington's head. So what is being done to protect Mount Rushmore? The cracks are being sealed with a special material to keep the water out. The material has to remain flexible so that it can shrink and swell with the rocks as they cool off and warm up. If the water is kept out of the cracks, ice can't form in them. And Mount Rushmore will be preserved for many generations of visitors.
Iggy, can you guess what else can make the cracks in a rock bigger?
More ice?
Actually, I'm thinking about plants and animals. Have you ever seen tree roots lifting or breaking up a sidewalk?
Oh, yeah.
Once a small root gets into a crack in a sidewalk or a rock, it can push outward very strongly as it grows. This can easily widen the crack.
But animals don't have roots. How do they break up rocks?
Animals, like prairie dogs and mice, dig their homes into and between soil and rocks. These holes allow the temperature and moisture to affect the rocks more. The holes can also cause rocks to break loose and roll downhill. So, Iggy, do you think you have all the data you need on physical weathering?
Let me check my memory banks. Physical weathering breaks rocks into smaller and smaller pieces because of abrasion, temperature changes, ice, plants, and animals.
You've got it.
So what's chemical weathering?
Chemical weathering is the changing of rocks into new substances.
Whoa! What powerful forces can cause rocks to change like that?
Well, take water for instance. You might be surprised to learn that water is responsible for a lot of chemical weathering.
I thought water worked on rocks through physical weathering.
Well, it does both. Have you ever seen sugar melt away and disappear in water?
Sure.
The water dissolved the sugar. The sugar is still in the water. You can even taste it.
Water can dissolve sugar, but it surely can't dissolve rocks, right?
Actually, it's what's in the water. Maybe this will make it clearer. Water can dissolve more things on Earth than any other liquid. And in nature, water often contains small amounts of other chemicals called acids. Acids are chemicals that break down or change other things. Some strong acids can even dissolve metal. So many of the minerals that make up rocks will very slowly dissolve in water with a little acid in it. However, some rocks dissolve much faster than others. This can be shown through a simple test. Place small granite pebbles in a jar and a piece of chalk, which is limestone, in another. Add a little bit of water to each jar. If you were to let the chalk soak in the plain water for many days, the water would actually change the chalk a little bit. But let's speed things up. Add some carbonated soda, which contains a weak acid, to the water in both jars. You will see bubbles begin to form as the acid reacts with the chalk. Let your jars sit for a few days and you will see that the acid in the soda dissolve most of the chalk away. The granite, however, will not show any visible effects from this acid. Though weak acids in the water will dissolve the granite, the process takes many years. Carbonation is what makes the bubbles in soda water. And it also makes the weak acid that dissolves limestone. That's why you get those crazy limestone formations in some caves. The water that soaked into the caves had this acid in it and dissolved the rocks slowly over many years. Some acids found in plants can dissolve rocks.
I thought plants, their roots, caused physical weathering.
Sometimes plant roots can cause rocks to break apart, which is physical weathering. But other times, plants like these can give off chemicals that slowly change the rock, causing it to break apart. Well, we've now learned a lot about chemical weathering.
Which can be caused by water and acids.
Yes, but now it's time to see how the weathered pieces of rock get moved.
That would be by erosion and deposition.
Right. As we said earlier, erosion is the movement of rock to new locations, and deposition is where these pieces of rock are placed after erosion. Weathering breaks down landscapes, erosion carries away landscapes, and deposition creates new landscapes somewhere else. This cycle is constantly reshaping the surface of the Earth.
So what causes erosion and deposition?
Wind, running water, waves, and glaciers.
We've seen some of those before.
That's right. The same forces of nature that cause weathering also cause erosion and deposition. So how do you think wind causes erosion and deposition?
Well, I know that wind can blow sand and dirt around. So I guess when wind moves sand or soil, that's erosion.
That's right. And when the wind stops, the stuff that's been blowing around drops in a new place. That's deposition. This can happen in plowed fields. And it provides one of the most powerful examples of erosion in deserts and at beaches.
But I'll bet the most important force of weathering, erosion, and deposition is water.
Yes, my friend, it is water. Running water, to be exact. When rain falls and the soil can no longer soak up any more water, the rest flows away on top of the soil as runoff. If the soil is not protected by plants, lots of heavy runoff can cause the soil to be carried away. This runoff can dig out big ditches and pile up layers of mud in other areas fast. Streams form in these ditches if the water flows often enough, widening the ditches and moving the rocks and soil far away.
I'll bet the same thing happens with rivers.
That's right. Rivers are the greatest source of erosion and can move huge amounts of rock and soil. The Grand Canyon, for instance, was formed by the Colorado River, slowly eroding the earth.
So where does all the rock and soil end up?
Where rivers slow down and widen, they are constantly depositing the rocks and soil that they have carried away from other areas. Where these materials are deposited, new land is formed. This can be at the sides of the river or where it meets the ocean, at an area called a delta. Waves are powerful movers and shakers as well. They move all the time, gently lapping the shore or crashing into it. First, this causes weathering, then erosion, and finally, the rocks and sand are carried out into the ocean and deposited on new beaches. Erosion and deposition can also be caused by ice. And not just any old ice. We're talking about giant moving sheets of ice.
Giant moving sheets of ice?
Uh-huh. They're called glaciers. Glaciers build up year after year if winter snows don't melt completely in the summer. Each new layer of snow packs down into ice, and the ice can move downhill. Moving glaciers can crush and rip up huge amounts of rock and move it to new places. Let's take a closer look at how this works.
As glaciers move and melt, they can alter the landscape. In today's demonstration, we'll build a small model glacier and see how it can affect a model landscape. Remember, this will be a simulation and won't be exactly the way real glaciers work. For this demonstration, you'll need a baking pan and some wet sand. These materials will be used to make your landscape. You will also need to create your model glacier. For this, you'll need an empty milk carton, scissors, some small rocks, some water, and a pad and pencil. Before you begin, have an adult carefully cut the top off the milk carton. First, place some small rocks in the bottom of the carton and then fill the carton about half full with water. Place this in a freezer until the water has frozen solid. Now, pile up your wet sand in the baking pan, creating a cone-shaped mountain. Pack the sides of your mountain tightly to create a firm surface. Remove your frozen glacier from the milk carton and place the block of ice near the top of your sand mountain. Be sure the small rocks are on the bottom side of the ice next to the sand. Now we'll let our glacier begin to melt. What do you think will happen as it does? Observe the glacier over the next couple of hours. Record what is happening to the glacier and the mountain. As the ice melts, much of the water will soak down into the sand. However, some of it should run down the side of the mountain, carrying away some of the sand and creating small riverbeds in the mountainside. This is erosion from runoff. This sand is also moved to new locations and left there, deposition. Depending on how tightly the sand mountain was packed, your ice may slide some distance down the side of the mountain as it melts. As the ice moves, the glacier will push sand ahead of the ice. Finally, when the ice has melted, you'll find the small rocks left behind. If the ice block moved while it melted, the rocks will have moved with it. They will be left in different locations from where they were first placed on the mountain in the block of ice. This is deposition. The rocks have been deposited in a new location.
Many glaciers dig out valleys and often make lakes when they melt. For example, the Great Lakes of North America were formed by melting glaciers.
You know, I thought weathering was impressive. But that was before I knew that erosion and deposition could dig out canyons and create new land formations.
But remember, Iggy, all three stages work together. Once weathering breaks down the rocks,
Things like wind, runoff, rivers, waves, and glaciers take the rocks
and soil.
to new locations.
So now that you know about weathering, erosion, and deposition, can you think of some problems and benefits these things give people?
Well, maybe one problem would be soil erosion. People can't grow the crops they need for food without soil.
Very good. But on the other hand, rich new soil can be deposited by rivers along their banks and in deltas. In fact, river deltas are where some of the best cropland on Earth can be found.
Then there's always blowing sand. It can cause physical weathering and bury things under sand dunes.
Right, but sand that piles up on the seashore helps protect the shoreline and the homes on it from waves.
It seems like every part of weathering, erosion, and deposition has its benefits.
Yep, it certainly does. Remember, they are all part of a process that's been going on for a very, very long time.
The cycle of weathering, erosion, and deposition.